Okay, folks, for this screencast, I'm going to talk about phase portraits. To sort of highlight this, what I'm first going to do is I'm going to build a simple spring mass damper system code, and we're going to plot some stuff. So I'm going to do, let's see, function phase portraits, and then function, I'm going to do dxdt is derivatives of x comma t, and then I'm going to do, let's see, I'm going to do x, I'm going to do state here so that like the input is like the entire state vector. And then x is going to be state of 1, and then x dot is going to be state of 2, and then x double dot is negative k over m times x minus c over m times x dot. And I'm going to do unforced here. K I'm going to be 10, c2, m1. It's really not important. So those are the equations of motion. Then I'm going to make some initial conditions. So x initial is, I'm going to do 0, 0 just to make sure that the code is actually running properly. So I'm going to do a t out, x out, or state out, sorry. State out is what, ODE 45. So I'm using the ODE toolbox. I'm telling it what derivatives function I want to use. I need to give it a t span. So I'm going to say to simulate for 10 seconds. And then the initial conditions. Now I might be wrong here. So I'm going to type in edit ODE 45. Oh, no, I don't want to edit it. Oops. I want to help ODE 45. Let's see. And so you give it the name of the derivatives function, the time window, and then the initial conditions, and then it will simulate that for you. So I'm going to do a close all up here and CLC. I'm not going to do a clear because I don't want to clear everything, and then I'm going to plot. Oh yeah, in MATLAB you have to do this. I've been coding in Python too much. So you're going to do t out and then state out just like that, and then let's see if that works. Okay, so I probably have this backwards. Try that. Did it work? No. Oh yeah. It says the d state dt is not defined. I forgot to put that in here. D state dt is x dot and then x double dot. All right, there we go. No, stop. F5. And okay, cool. So we got everything 0. All right, so we're going to give it an initial condition. So I'm going to perturb it 5 meters, and then okay, cool. So then there's the state x and then the velocity in red. Okay, so we're getting what we're getting here. Okay, so this is plotting sort of with respect to time, but if I want to make a phase portrait, or really if I want to plot in the phase plane, what I want to do, I'm going to drop a new figure down, and I'm going to plot x out is state out. What's the size? Oh, I don't know. All right, I'm just going to have to guess. I think it's all comma 1, and then x dot out is state out, all comma 2. And I'm going to plot x out on the x-axis, but then I'm going to plot x dot out on the y-axis. And did it do it? There we go. Yeah, sweet. So there's my initial condition, perturbed along the x, and then x dot, the initial condition is 0, and it sort of circles down into the origin. Okay. So that's in the phase plane, and so this sort of shows the system and how it decays down to 0. There's the equilibrium point, or the stationary point, or the singular point, however you want to call it, is right there at the center. In order to create the entire phase portrait, what you have to do is loop this entire thing. So I'm going to say for x0, and I'm going to go from minus 10 to 10. I'm going to go in 0.1 increments, and then for x dot 0, 10, minus 10, 0.1, 10. This might be too many, but you know, it is what it is. So instead of making the initial conditions constant, I'm going to make it a variable. T-span I can put up here because it's the same. I want to simulate every time in this loop. I don't want to plot with respect to time anymore, but I do want to plot the phase plane. This figure needs to get moved up here because I want to plot one figure. And then I can put this here, and then I need 2 ends, and then I need to throw a hold on so it plots over and over and over again. And so that will probably take a long time to run. Honestly, let's make sure this is working right. Yeah, that's a lot. Let's do let's do 1. So we're going to step in increments of 1. And then let's do, just for kicks, let's do a draw now so we can watch this in real time, because this is going to be kind of cool. All right, so those are all the derivative, or the sort of the initial conditions as it's simulating. And there we go. There's the phase portrait right there. So basically every single one of these is a trajectory of initial conditions as it goes down to the origin. And this is a stable equilibrium point. I can change the sort of the stiffness and damping. So if I made C0, what would happen is that my system would go into a limit cycle, right? Where now you have a situation where the system just kind of spins around in circles and never decays down at the origin. And the reason why it does that is because the eigenvalue, one of the eigenvalues goes to 0, essentially. What you can do, which I think might be more beneficial, is if you put this thing in state space form. So if you get rid of this and you say, make my A matrix 0, 1, negative K over M, negative C over M, like this, and then you made, let me do it, undo, let me leave that there just in case. And then you did d state dt was A times the state, right? So at that point, you're in state space form where you're multiplying by a matrix. Well, if you take this matrix here and you throw it in here and it'll let me do it, and you look at A and you type in EIG of A, I'm sorry, I said one of the eigenvalues went to the 0. The eigenvalues actually went to plus or minus 3.16i, and so it's actually it's purely oscillatory motion, right? So it just oscillates over and over and over and over and over again and never decays down to 0. If I add a 2 in here and simulate this again, and while that's running, if I copy this and throw it back over to here and hit enter, and it's probably still integrating in the background. Maybe not. Okay, so there's A, and so I type in EIG of A. Now, see, I have a real component, which essentially brings me in, and then an oscillatory component. If I critically damp the mode, so I have to remember how to critically damp a mode. So if your second order system is, S squared plus 2 times zeta times omega n plus omega n squared, I think omega n, what I need to do is put m up here, and then omega n is going to be square root of k over m. And then if zeta is 1, and I think I have to do z because I think that's a built-in MATLAB function. If zeta equals 1, then c is 2 times z times omega n. And I think that will be critically damped. And again, yeah, it definitely is, because you see that the system essentially doesn't oscillate anymore. It just critically damps down to the origin, the equilibrium point. If I copy this and drop this in here, and I look at A and I type in EIG of A, you'll see that I basically have 2 modes there. If I make Z5 and then run this, you'll see that now I've got a situation where the system, it's not critically damped, it's completely overdamped. And so if you look, there's this line here that that the system sort of decays on, and that is actually the eigenvector of the system. So if you type in, if you grab all of this and you hit copy and then A, if you do EIG of A, you'll get that the system is overdamped for sure. But if you type in S comma V equals EIG of A, you'll get the eigenvalues right here, and then you'll actually get the eigenvectors here. And so if you look at this, if I zoom in to the origin right here, okay, this is saying that if I march along the x-axis 0.95 and then march along the z-axis 0.3, right? So if I go, that's 1, so 0.95 is like here, and then if I go negative 0.3, that's exactly along this line. So this line here sort of essentially tells you sort of the line where the system will just perfectly go along that. It's just like perfectly damped that will get you along that point. Okay, so that's linear phase plane analysis. So what I wanted to do then now is talk about nonlinear phase plane analysis. So if you take your this is a sort of the mass spring damper system here, and it is linear and everything's all well and good. If you go back and you say, okay, forget about x and x dot. If I take theta and theta dot and say that theta double dot is negative g over L times sine of theta. So this is a pendulum, and I say g is 9.81, and L I'm just going to make as 1, no big deal. And then d state, dt, I have to go back to sort of a nonlinear model and say theta dot and theta double dot. Okay, so if I run this, oh gosh, did I make it unstable? What's going on here? Oh, you know what's happening? I made the initial conditions go from -10 to 10. That's kind of, let's go from, let's see, so this isn't x0 anymore. This is theta 0. So do I want to say like -2 pi? Let's say -2 pi. And then let's say 0.5 to 2 pi. And then I think -10 to 10 I think is fine. All right, let's try that and see. Okay, no, it's still, so it looks like this is going 10 to the 4th. It looks, oh, okay, yeah, I just have a bug in my code. That's supposed to be state 2. Okay. All right, now we're talking. Okay, so now we're getting some super weird things here, right? So we're doing initial conditions from, what, minus 2 times pi? 2 times pi should be 6.28, right? I think this is working. I think what happens is that for some of these initial conditions, the angular velocity is so large that that's what's happening. So right here, oh, there's no damping. So these are just stable limit cycles. That's what's happening. So see, if you take this trajectory right here, you are right at minus pi. So you're in the inverted pendulum scenario. But your angular velocity is positive, and so you end up doing this oscillation where you just keep jumping over and over and over again. And the reason why it extended out, the reason why this went out to infinity is because it essentially just like kept bouncing over and over and over and over and over again. And so here, this is a scenario where the angular velocity was so high it just went on forever. So let's add some damping in this. So let's say minus, I'm just going to make C10, C times theta dot. Okay, so that's going to add some damping in the system. Okay, so I clearly like over damped the system. So let's make not C10, let's do 0.1. Just give me a little bit of damping. How do I kill this? There we go. Okay, so now I feel like my trajectory should like sort of come back into 0. I feel like 10 is too. Let's do -1 to 0.1 to 1. Because it's getting kind of crazy plotting this. Now we're talking. Yeah, no, I like this. Okay, see, sweet. This looks really cool. Okay, so what you're seeing here is that if you are inside this bubble, right, in here, so if like the norm of your initial condition vector is inside this bubble here, all of your trajectory will tend towards this 0 component, right? But if you are outside this bubble, right, and it's hard to see because I didn't go, doesn't look like I went high enough. So let's see if I can go a little bit higher. So instead of going, let's do 3, so you can kind of see what happens here. Okay, so these are all the ones that sort of get trapped in the bubble, and let's see if any of them break out. Yeah, okay, it happened here. All right, still rendering like crazy. See, so here, I'm pretty sure this trajectory right here, right? It could have gone into this bubble, but it actually hopped over this point, came over here, the angular velocity practically came down to 0 and slowed down, but then bumped around. And if we would have simulated long enough, it would have essentially decayed down into this point in here. Okay, wow, this simulation is like still going. This is wild. But what you're seeing here is you're actually seeing sort of this oscillation where you have an equilibrium point here, 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 and here. And if you look at these numbers, you have one at 0, one at 2 pi, one at minus 2 pi, and so you have these here and here. But here in this quadrant here, you actually have singular points in here, but they're unstable. And they're actually saddle points. You actually have a region. If you look at these trend lines, and you zoom into this equilibrium point, see this line, these tend directly in towards it. So if you were on this line, if you had the perfect initial condition where you were on this line, you would tend here and stop. Anything else is going to be just to the left or just to the right, and you're going to bounce out and go out the other way. And so this eigenvector this way is unstable, and then this eigenvector is stable. Okay? Now this is all nonlinear, so how do you put this into a linear sense to get an idea of what's going on, right? So if you say your A matrix, if you linearize this, it's pretty easy to do by hand, but you're going to get minus G over L times cosine of theta 0, okay? Where theta 0 is your equilibrium point, and then you're going to get just minus C over here, okay? Now, if you do theta 0 is 0, okay? I think I did too many points here. Let's do minus 2 to 2 to get half the number of points. I didn't like it because it said theta double dot is not defined. Oh, okay, so then the difference is you need to go back to the linear model and say D state is just a state. So if you simulate this, and actually, I need to compare apples to apples. We got to do minus 3 to 3. Let's just do minus 3 to 3x and do 0.2. Okay, and see if this will run fast. And you know what? No, it's fine. It's fine. It's fine. It's fine. It's fine. Okay, but basically, I don't know if you can tell what you're seeing, but even when you're over here at 2 pi, every single one of the equilibrium points goes to the center. And that's weird, right? Because the nonlinear model, we had multiple equilibrium points, but the linear model, everything kind of got thrown out the window. And the reason why is because you've approximated the system as a linear model. And so if we look at this, if we do a copy and a paste and look at state, well, I still have A. If I look at EIG of A, this is saying that I have a stable equilibrium point everywhere. It's saying that my system is globally asymptotically stable. Now, that's not true in the nonlinear model, but we linearized it around that point. And so really this system is only valid around this region of the equilibrium point. If I then go back and say, hey, you know what? Let's make this pi. Now we're going to get something completely different. Now, what's interesting is that if I make the equilibrium point pi, because I'm linearizing the system, it's still going to assume that the equilibrium point is 0. But that's because, remember, when you linearize a system, you get dx dot is partial f partial x times dx, where dx is x minus x naught. So if the equilibrium point is 0, then there's no offset. But if you put pi in there, you have to add pi to the other side. So we could go up here and add pi to it, but I don't really care about that. But the point is if you run this, now you're going to get a much different picture. And you know what? I think I need to restrict my axis window. Let's say axis, negative 10 to 10, 10 to negative 10 to 10. There we go. See now, because it was trying, some of these went all of these went unstable, right? And so it was essentially trying to get the window in the entire thing. But here's the equilibrium point, and so now you're starting to paint a picture of what's going on here. And if you zoom in on this guy, if it'll let me, oh no, it's because it's restricting it. We have to wait till it's done plotting. How far did we go out to? We went to 2 pi, so we're almost done. Okay, it just finished. So if we zoom in on this guy, here again is my stable eigenvector and then my unstable eigenvector. And so let's see if we can actually determine what those eigenvectors are. So if I copy this, paste it in here, and then again, if I do EIG of A, I'm going to get one positive and one negative pole, which is totally fine. But now what I want to do is I want to say, okay, give me the eigenvectors. And so now I've got this eigenvector here. So this is associated with a positive pole, so that's the unstable one, but I really care about this negative stable eigenvector here. So if I go, let's see, negative 0.2 along the x-axis, negative 0.3 along the x-axis, and then positive 0.95. So let's see. This is, it's hard to see. Can I throw a grid on this? Is that allowed? Yeah. All right, let's zoom in. So if I go, so this is 0.5, so this is 0.25, so 0.3 is about here, and then what, 0.95? You know, can we just draw a dot on there? Let's just do that. I'm going to do plot negative 0. Okay, I don't need the help. 0.2998 and then 0.9540, and then I want you to draw a blue star with a marker size of 20. Boom, there you go. So see, there is your stable eigenvector where all the trajectories, if you're perfectly on this line, you will go right to this point. And so that's interesting too, right? So if you I wonder if numerical precision would be able to handle this. But if you simulated this with that exact point, you know, honestly, with numerical precision, it would probably get there and shoot away. That's just how unstable this is, like, in a perfect world, right? Because if you did format long G and you just looked at S, I mean, this is your initial condition, right? I mean, that's ridiculous, right? There's no way that would ever work. I think the only way it would work is if you made G like a perfect number or whatever. So when you did square root, I don't want to kill this. Let me look at this. So if you did that, because then square root of G over L would be a number that made more sense. So if you did S comma V of A, EIG of A. No, you still get something weird. Yeah, I don't actually know how to get this to work. It would, you end up getting really weird numbers there for sure. Actually, the eigenvalues, that's kind of, is it because of the damper? The damper's in there. So let's do this again without the damper. Okay, so now my eigenvalues will make more sense. So can I do EIG of A? Dang it. Unfreaking believable. Okay, well, I tried. All right, well, I think at this point, I think I've exhausted this video here. How long am I going on here? Like 22 minutes? Yeah, I think that's a long time. I think if you just watch the first 10 minutes of this video, I think the only other thing that I could probably talk about is sort of the difference, you know, plotting a nonlinear phase portrait and a linear phase portrait, and I kind of did that already, right? So if you comment this out and simulate the system with nonlinear, you'll pick up all of the different equilibrium points. But if you linearize the system, you're only going to pick up the one equilibrium point that you stabilized at. Okay, well, hopefully that helped, and happy coding.